Okay, it's great to see such a new crowd. About 3/4 of people here haven't been to CFI before, which forces me to tell you what CFI is, unfortunately. Not the funnest part of my job. So the Center for Inquiry, it does a lot of science. We promote science and a scientific outlook on life. We also promote reason, freedom of inquiry, and secular values. And we do this through a variety of means. The Voices of Reason lecture series, which you're here tonight, which is part of our ongoing lectures. We do it every 2 weeks. This is kind of our big ticket item. We also do film screening once a month. We do a book club. The next film is going to be in late March. I forget the name of the film, but it's about skepticism and magic, so it should be quite interesting. And then we're doing a book club in March as well on Philip Pullman's that trilogy of books, his Dark Materials, The Golden Compass being the first book that we'll be discussing. Coincidentally, if you're in Oakville and you watch the local radio or the local TV, I'll be doing a piece from 8 to 9 Monday night on that book in particular. What happened was, as you may know, a couple of Catholic school boards tried to ban them. In any case, one of them actually did, but the Halton, the Oakville school board actually decided not to ban it. So they just came out and announced this, and it's news again. So I'll be on just defending why that's a good idea. So we do things like political outreach, obviously, and social services and stuff like that. A couple of big announcements that I wanted to put out there on behalf of CFI. We're launching, or we have launched, an allied organization to do strictly political advocacy defending secularism, science, and reason. It's called the Canadian Secular Alliance. You might be interested in finding out more about that. Some people here that are involved in that as well. Also, we're looking for volunteers. Those of you interested in supporting what we do, we need web designers, graphic artists, promotion experts, just general administrative staff to help us out on a weekly basis or thereabouts, so you can ask me for more information on that. Another interesting announcement is that we're moving into Montreal. We're establishing a CFI community for inquiry in the city of Montreal. We'll be doing that in the next few months. And to support that, we'll be hiring a part-time staff member to assist me here in Toronto, so things are really progressing nicely. If you want to help out with all this great expansion of this free thought movement, pledge to CFI. Help us out financially, become a friend of the center. That's the number one thing you can do. It's $20 for students, which gets you to everything we do for free. We do one of these big events basically every week or two, so it's quite worth it, I think. $60 for non-students, and there are low-income options for those of you for whom that applies. And if you want to donate in excess of that, of course, we welcome that. So I'll put that out there, and do consider that strongly. If you would like to do that today, we can reimburse you tonight's event, put that towards it. The last thing I'm going to say is there's a big event next week as well, which I'll tell you more about after Dr. Orr's talk. There is a book right here which you can take a look at in advance, The Secular Conscience. That will be our next big event next Friday. And also, as part of this ongoing series next month, we have Amanda Peet talking about string theory, part of the Future of Science series. So with that, I think I will move on and introduce our great speaker for this evening. We have with us Dr. Robert Orr, who is a professor in the Department of Physics at the University of Toronto. I think many of you know him perhaps personally. He was NSERC Principal Investigator for ATLAS Canada from 1994 to 2007, ATLAS being a detector within the Large Hadron Collider at CERN, and one of Canada's principal contributions to the project. Professor Orr is a Fellow of the American Physical Society and the winner of a 2006 Orion Discovery Award of Merit, Orion being the Ontario Research and Innovation Optical Network. So, quite a prestigious speaker, and we look very, very forward to hearing about the LHC and all the wonders it's going to bring to light. Dr. Orr.
All right, thanks. I'm not sure if I actually need the microphone, but if you can't hear me, you should shout down and say, I can't hear you. So what I'm going to talk... Sorry, you already said that?
I don't know if they can hear you.
Is the microphone working?
Here, we'll move it close to you.
No, it's okay. I'm sure it's okay because I walk around. It has to be okay. So what I'm going to talk about is what we think the universe might be made of. And I'll talk about things like the Higgs boson, dark matter, and supersymmetric particles, which you may or may not have read about in the weekend newspapers. And the thing we're building in Geneva to try and investigate some of these issues is a thing called the Large Hadron Collider. And I'll talk about this in some detail and show you quite a few photographs of it. But this is just a cartoon to introduce it. And it's a big tunnel which is 27 kilometers around. And this is a cross-section of it, with a physicist standing inside it. and the protons are bent around in a circle by these intense magnets. And the experiment I work on, this is a cartoon of it, it's called Atlas, and it's a giant thing. These are a couple of people down here, and this is one of these big dump trucks that they use in the mining industry. So that's just the introduction. What I'll try to talk about is what we think visible matter may be made of, what we call the standard model, which is our understanding of it, and I'll talk about quantum forces and a little bit about the unification of forces. And I'll assume that people don't know anything about that, although I know that there are some people here who are already very expert in this subject. And then I'll talk about the cosmological evidence for invisible matter in the universe, something called supersymmetry, and then this Large Hadron Collider. Do you really need to have it as close as that to me? Yes. It's like Cookie Monster or something. So, you've probably heard that matter as we know it is made out of quarks and leptons, and there is what we call three families or generations of quarks and leptons. There's the up and down, the charm strange, and the top and bottom, and these are what we call quarks, and they see the electromagnetic force, they see the strong interaction. And then there are things called leptons, the neutrinos, which are very evanescent particles, and things like the electron. The electron is the lightest of the leptons. And then there are these particles that carry the forces between these matter particles. So these are what we call matter particles, and these are force particles. For example, the familiar electromagnetic force is carried by this guy called the photon. The strong nuclear force that holds the protons and neutrons inside a nucleus is called the gluon, and there are these rather weird ones called the Z and the W. Now all the matter that we know about in the universe, although I'm going to say in a minute that that's not true, all the matter we think we know about in the universe is made up of and down quarks and electrons. So you might ask yourself, why in the world, just after the Big Bang, were there actually three generations? And you can ask yourself that, or you can ask me that, but actually nobody knows why there are three generations, although maybe we have some ideas on it. So for example, the way these quarks are put together in the universe today, an up and a down quark, as many of us know, makes a proton, and they're held together by gluons, and a neutron is an up, a down, and a down quark. And I haven't told you the electric charges, but because that's probably too much detail for this evening. But this arrangement is because of what we know about the electric charges of the proton. Now, you're all used to the idea of a force, and one of the forces that you're used to the idea of is taking a fridge magnet, and when you get close to the fridge, you feel this invisible force pulling the magnet onto the door of the fridge. And what's going on there, as far as we understand it, is that the magnet is exchanging what are called virtual photons with the door of the fridge. These are the carriers of the electromagnetic force. So in quantum field theories, we call it, the relativistic theory of quantum mechanical forces, we imagine all forces as being transmitted by particles, virtual particles as they're called, jumping from one particle to another. So when an electron jumps to another electron, and the analogy I give for that is if you take a piece of paper and you rub it on your cat, it becomes electrically charged, and you can sort of lift your cat's hair up with a piece of paper. And what's happening there is that the electrons on the cat are attracting the protons on the piece of paper, and they're doing that by exchanging these virtual photons that you can't see. And in a completely analogous way, the quarks inside a proton exchange these characters called gluons, the carriers of the color force, which glue the quarks inside the protons and the neutrons, and thus make up matter as we know it. And how can this happen? How can these virtual particles, as they're called, jump from one particle to another? Well, it's a complicated thing, but you can sort of understand it if you've heard of Heisenberg's uncertainty principle, that for a very short time, well, that you can violate energy for a very short time if the violation of energy and the time you do it in is of the order of Planck's constant over 2 pi. So essentially these virtual particles use Planck's constant to borrow energy from the universe, and they have to pay it back in a time delta t. And by jumping around from particle to particle, they produce all the forces that we see in the universe, apart from gravitation. Now there's another force that I have to introduce, so I'll introduce the electromagnetic force, the nuclear force, a strong force, or chromal or color force as we call it. But there's also a very interesting force called the weak interaction. And if you looked at these little diagrams of the particles throwing virtual bosons, virtual quanta between them. You can't see this at the back of the room, but the virtual particle jumping across between these lines is labelled a W or a Z. Now, we understand now that electromagnetism and this weak force mediates, for example, beta decay. It mediates radioactive decay. So all the nuclides which are decaying in the reactors and the power stations down the lake, they're actually doing it by using W and Z bosons to emit electrons and neutrinos. It's called beta decay. And over the past 20 or 30 years, we've understood that electromagnetism and this weak force are actually the same force. And it's rather strange because electromagnetism has got a massless particle and the weak force is mediated or carried by these massive particles. And that's one of the most interesting things that we've understood. I won't talk about that we've understood in the past 3 decades. And that is that the fact that we can unify the electromagnetic and the weak force, and I'll talk about what unification means in a minute, implies the existence of a particle that no one's ever seen. So for example, if you take these W's, which carry the weak force, they actually have electric charges on them. So they can interact via the electromagnetic force. And in fact, all these interactions, when you try to calculate them, they give infinite results. And that's very depressing because electromagnetism on its own gives proper results. But any calculation you do in physics that gives you an infinity must be wrong because you don't find infinities in the real world. You only find them in mathematics. So these infinite contributions become finite if we suppose that there's another particle. And it's a complicated mechanism which I shouldn't try to go into tonight, but basically we say there's a thing called the Higgs boson, and by the fact that these W's with their electric charges can exchange virtual Higgs bosons, this is infinite, and this is infinite, and these two infinities cancel out, and the whole thing comes out right in the end, which is very nice. The other thing which is interesting is that in the theory you build with these Higgs bosons in it, these Higgs bosons, they give mass to the W and the Z0, but they don't give mass to the photon, and they generate the masses of all the quarks and leptons. So this Higgs boson is a very fundamental thing in the universe. Mass is probably one of the most obvious things that about matter when you look around you. Now, if you know a little bit of high school physics, you'll understand this analogy, but if you don't, it doesn't really matter. It's how does this Higgs boson generate mass? Well, you know, photons which are flying through the vacuum, you know, they're particles of light. They're coming from these lights on the ceiling. The light you see is many, many photons coming down. And by definition, these photons move at the velocity of light. And they can move at the velocity of light because of zero mass. Now, if you know anything about optics, say you're an optician or you make spectacles or you're an astronomer, you know that in glass, a photon actually travels at less than the velocity of light. And the reason it travels at less than the velocity of light is that the electric charge of all the electrons in the glass affects the behavior of the photon. It slows the photon down. And in our parlance, it gives the photon an effective mass. This is what's called refractive index in optics. Now, what we imagine is that just as a photon traveling in glass is traveling slower than the velocity of light in a vacuum, any particle traveling through space-time is traveling slowly because it has to fight its way through this Higgs field. And that's what we call mass, inertial mass, is actually the effect of all the quarks and leptons. They have to propagate through this background Higgs field in the universe. So obviously the Higgs field is a very important thing. And one of the things about quantum mechanics or quantum field theory is that whenever you have a particle, you have a field that goes with it. Or if you have a field, you have a particle that goes with it. You're used to talking about the electromagnetic field of light. And I've just told you that there are photons. So if I say that there's a Higgs field in the vacuum, that means that there must be a Higgs particle. And that's what the LHC is all about, is to try and find this Higgs particle. Because if you take a little region of space-time and you put enough energy into it, you can actually create real Higgs bosons, if we're right. If we're wrong, you can't. Another concept that I wanted to introduce is called grand unification. So I've talked about these three different forces: the electromagnetic force, that goes with the fridge magnets and your cat and whatnot, the weak force that goes with the beta decay in nuclear reactors, and the strong force that holds all the quarks together inside the protons and the neutrons. Now our theories at the moment indicate to us that at some very high energy scale, all these forces are the same. The strong force is called strong because it's strong. The weak force is called weak because it's weak, and this is EM down here. So as you go up in energy, all these forces come together and have the same strength. So they're not different forces anymore. They're exactly the same force. And this energy scale is actually, it corresponds to the lifetime of the universe. So if I go along this energy scale, what I'm doing is I'm going back in time. So if I can increase the energy scale on some piece of space-time, I can recreate the conditions which existed at the beginning of the universe, at the Big Bang. So we believe very strongly that something happened in the universe after the Big Bang. So there was a Big Bang, and then the universe started to cool down. And this cooling down has made the primordial force, the single force, appear to us as if they're different forces. In sort of complicated parlance, the universe has gone through what are called phase transitions. And you know what phase transitions are, because if you start off with steam, you go through a phase transition when you produce water, and you go through another phase transition when you produce ice. And the properties of ice are very different from the properties of steam, but it's still the same stuff. And what we believe is that the properties of these gauge forces, as they're called, were very different early in the universe, but the universe went through these phase transitions. And what the Large Hadron Collider is trying to do is to reverse the first of these phase transitions. By analogy, the phase transition where the universe went from water to ice, we're trying to boil it back up again into water. We're trying to reverse, in very small regions of space-time, this first phase transition. So the way I'm talking, it sounds as if I absolutely understand the universe, which is not absolutely true. Because let's go back to this slide, and I said the first puzzling thing is that everything we see about us is made of these up and down quarks and electrons. So why in the world were there these charmed and top and strange and bottom quarks early in the universe? We know they were there because in accelerators before the LHC, we've put energy into little areas of space-time, and we've produced these quarks, which only existed very early in the history of the universe. Now this is a picture that you can't actually read, and you can't really read the scale up the side, but what it's supposed to show you is how the universe evolved from the Big Bang. So this is quantum gravity down here, and up here is a galaxy far away that we live in. This is about 10 to the minus 42 of a second after the Big Bang. This is about 1,000 seconds after the Big Bang, and this is about 10 billion years after the Big Bang. And what happened after the Big Bang was there were a whole bunch of exotic particles produced and a lot of energy. That's why it's orange and red. And all these particles were massless. And then the first transition that the universe and the space-time went through, all the particles gained mass, and they gained mass because of the existence of the Higgs boson. And if you're old enough, you've played a game called Pac-Man, where there was this little thing that ran around the screen eating up all the other little creatures in the computer game. And what these things here are Higgs bosons, because again in the parlance of physics, what these Higgs bosons are doing is they're running around eating up the extra degrees of freedom of all the massive particles and turning them into massive particles. You don't really have to know what that means. But anyway, after that has happened, all the quarks and leptons have masses, and the strong force starts to pull them together, and you produce neutrons and protons, which produces atoms. And this is all going on inside an enormous fireball, which is expanding. Then the fireball expands far enough, it becomes so tenuous that photons, namely light, can propagate across it freely. So this boundary here is called the surface of last scattering, and it's when the universe became transparent. Now, if you stand outside in the night and you look up at the night sky, what you see is the surface of last scattering. You see photons coming from the surface of this fireball, but you don't actually see them because the universe has cooled down so much that these photons are actually microwave photons. They're microwave radio waves. But you can hear them in a sensitive radio receiver. You can actually hear the hissing from the surface of the Big Bang. And in fact, the way it was discovered was that I guess it was in the late 40s, a guy called Penzias and his collaborator, they were asked to figure out by the Bell Telephone Company why all the microwave links had this hissing in them that people couldn't get rid of. So they took antennas and put them on top of the Bell Labs in New York State and sort of pointed the antenna around. And everywhere they pointed the antenna, they heard the hissing, because that hissing is coming from the birth of the universe. And that the temperature of that surface of last scattering is now about 2 to 3 degrees Kelvin. It's very cold. Okay, so everything I've said there implies that the universe is expanding. Huh? And the expansion of the universe was actually discovered by Edwin Hubble on Mount Wilson in California back in the early 30s. And as you've probably read all the stories about when Einstein first calculated the field equations of general relativity, he saw that the universe had to expand or contract, but he knew that it didn't, and he had to put various constants in to stop it doing that. And then about a decade later, Hubble observed that actually the universe was expanding. And the way he observed its expansion is you can see the velocity of galaxies in the universe just by looking at the redshift on them, by looking at the Doppler shift on the light. So when an ambulance goes past, you hear the Doppler shift as the frequency drops. And this is just the same thing. These galaxies are flying off from us, and because of their high velocity, the light from them is shifted into the red. And by looking at how much the light is shifted into the red, you can figure out what their velocity is. And it was amazing to Hubble that he found that the velocity of recession was exactly proportional to the distance from the Earth, which means that we were at the center of the universe. No, it doesn't actually, because you must know the analogy that if you take a big balloon or a small balloon and you paint dots on it, and you start to blow it up, then every dot on the balloon sees all the other dots moving away from it at a linear velocity. And this blowing up the balloon is like the expansion of space-time, the expansion of the universe. So we're not special. Everybody thinks that all the galaxies are receding from them. So, humans are fairly social creatures. And one of the questions you can ask yourself is, this thing is expanding. Are we going to be left on our own? If we go aeons off into the future, will the Earth and the solar system just be sitting in dark space and everything else has expanded off and we can't see it anymore? Maybe it will. You can figure out whether that will happen or not because if you know what the density of matter and energy in the universe is. For example, what's pulling the universe back together again? There's a big bang. And then there's something pulling the universe back together again, and that's gravitation. And gravitation comes from mass and energy. So whether the universe continues to expand or collapses back down again just depends on the density of energy and matter in the universe at the moment. And this is one of the few equations I'll show tonight. The fate of the universe depends on this thing called rho critical, rho c. If the density of matter and energy in the universe is greater than this critical density, the whole thing will collapse in on us at some point in the future. If the density at this epoch is less than the critical density, it'll fly apart forever. If it's exactly equal to the critical density, the universe will just slowly come to a stop in the infinite future. And if you're minded to, you can calculate the density in the present epoch as a ratio of the critical density. I call it omega 0, and it just depends on Newton's constant and the Hubble constant. Both of these you can measure. So if you want to know what the total energy mass density of the universe is, somehow you have to measure this density of energy and mass in the universe. And I've written down here, if omega 0 is greater than 1, you have contraction. If it's equal to 1, you have flat expansion. That's expansion that comes to a stop. And if it's less than 1, you have this hyperbolic expansion. But as I talk about it, you have in mind the idea that this expansion is slowing down. If you ever see an explosion, all the bits of it slow down after the explosion. Now, one of the interesting things about the world is that you can actually measure the total energy and mass density of the universe. And you can't do it by taking a little box and taking a bit of the universe and weighing it and looking at the size of the box. You can't do that. But what you can do is you can look at this fireball, the remnants of the fireball, and this was actually done by a guy at UT called Bart Netterfield. If you look up into the night sky, you see the temperature of the fireball, but you also see variations in the temperature. And these variations in the temperature of the surface of last scattering, this is then shown here. There's thousands of a degree Kelvin, but you can measure them. And these little variations in temperature come from the fact that there were pressure waves propagating through the fireball after the Big Bang. These pressure waves are essentially sound waves. And if you know the frequency spectrum of sound waves, you can measure the density of what they're moving in. So what these people have done, this is just to show you that the data is these dots from a satellite measurement, and this is a fit to them, and this fit tells you that the density of matter and energy in the universe back at the just after the Big Bang was equal to 1 times the critical. And if you believe in energy conservation, that means it's exactly the same now, because the energy can't have gone anywhere. I mean, the universe is everything. Now this is an odd number, 1, because any physicist looking at it says this density can be anywhere from plus infinity to minus infinity. Why on earth should it be equal to 1? 1 is probably the least probable number. You would expect it to be equal to 92.6345 or something like that. 1 is a very, very unlikely number. So where does this 1 come from? Well, I can't really go into where the 1 comes from tonight. It comes from the fact that there was this what's called an inflationary expansion of the universe, and that's sort of irrelevant for what I want to talk about. I want to talk about something different. And that is these quarks and leptons, we refer to them as baryonic matter. Baryonic matter means heavy matter. Baryon comes from the Greek for heavy. Now, if the whole universe is made of the stuff that we're made of, and the table's made of, and the computer's made of, namely quarks and leptons, then the density in baryonic matter, which is that matter, should be equal to the density that you measure in the surface of the Big Bang. Unfortunately, it's not, because you can measure the density of baryonic matter. It's a complicated thing, and you have to trust me a little bit on this. But by measuring the proportion of deuterium, helium, and lithium in the universe, and you can see that from the galaxies, you can measure the density of baryonic matter, and it comes out as 0.04. So that says that whatever the fireball of the Big Bang was made of, it certainly mostly wasn't made out of the stuff we see around us. The whole universe that we've observed up until now, everything that physicists and chemists and biologists and philosophers have studied, is only 4% of the mass of the universe. It's essentially an irrelevancy, that most of the universe is made of something else. So our first idea is there's some kind of dark matter. There's matter in the universe that we can't see. And in fact, it turns out that there is, because if you look at how galaxies rotate around each other, and how galactic clusters rotate around each other, and how galaxies rotate themselves, if you know classical mechanics, you can figure out the amount of matter that's there from what are called the rotation curves. And it turns out that the density of all matter affected by gravity is 0.26. So the matter we're made of is affected by gravity, but it's also affected by electromagnetism and the colour force and the weak force. That's how we see it. But there's 26% minus 4%, namely something like 20% of the universe is affected by matter, which is affected by gravity, but we can't see it. What I'm saying to you is that most of the matter in this, if you average over the solar system, most of the matter in it is not the stuff we're made of or the Earth is made of. It's this dark matter that all we see it by is its gravitation. We can't see it by light or the weak interaction or the strong force or anything else. Actually, it's quite alarming that this the total mass density of gravitating matter, so that's our matter plus the dark matter, only makes up 20% of the universe. 75% of it's something completely different. It's something we don't know anything about at all. People often call it quintessence or something like that, but actually, if you call it something else with the capital letters on the something else, that's as good a name for it, because it summarizes that you don't know anything. And I'm going to take, at the risk of running over time a little bit, I'm going to show you what sort of evidence there is for this dark energy, as it's called. That sounds like something out of the Lord of the Rings. There's something from the land of Mordor, the dark energy. Anyway, you know, I stand up here and I say to you 75% of the universe's mass and energy is made up of this dark energy, so I'd like to show you the evidence for it. But anyway, I'll show you that in the next transparency, because it comes from measuring the luminosity, the brightness of very distant supernovae. And essentially it shows us that in the past, the galaxies were moving apart more slowly than they are now. So a usual explosion, you'd expect the explosion occurs, then it slows down, but whatever made the Big Bang, this explosion is speeding up. The expansion of the universe is speeding up, and it's being driven apart by this dark matter. Anyway, this is my calculation where I take the 26% with the error bar on it and 75% with an error bar on it, and I find that the total density of gravitating matter plus the dark energy gives you 1, and that's the 1 that the omega z that the omega 0 that you measured from the surface of the fireball. I thought I'd just show this because it's interesting. The way there's a guy called Perlmutter from Berkeley led the group that discovered this, and a supernova, its light comes up and then dies away with a characteristic sort of speed or a characteristic time dependence, which tells you what the absolute brightness of the supernova is. So if you look at a supernova in some far-off galactic cluster, you can't tell. You either have to know the brightness of the supernova, or you have to know how far away it is. And we don't know either, because we see it with the light attenuated by coming through space. But because you can look at the time variation of the light coming from the supernovae, you know exactly how bright they are.